Hello and welcome to this Chemistry World webinar, Optimizing Protein Stability Using New Computational Design Approaches for Biologics. I'm Phillip Broadwith, Chemistry World's Business Editor. For those of you who are not familiar with the GoToWebinar platform, just to let you know, GoToWebinar is interactive. You can ask questions of our speakers at any point, and that's one of the key things about the webinar function. The interactivity. There's a box near the bottom of the GoToWebinar panel. By default, that should be on the right-hand side of your screen, but it might move around a little bit. You can just type in any questions you might have. The questions are a really important part of the webinar, and that's where we see the most value for our audience. So please do ask away. Don't wait until the end, because we're likely to get quite a lot of questions coming in at the end. So if you get your questions in early, it allows us to see what's coming in and prioritize things a little bit better. So please do ask your questions at any point as they occur. If you do miss any part of the presentation, or you just want to watch it again in your own time to pick up on some details, see the links again, or check out some of the resources that we're kind of highlighting, then we will be sending everyone a link to the recording in a few days' time. And just to say thank you to everyone who's attended live in the webinar, you will also get a certificate of attendance in that same email. So today's webinar is about using physics-based free energy perturbation methods to accurately predict protein stability, with particular reference to biological medicines. To be successful, protein-based drugs, vaccines, diagnostics, or enzymes, they need to be stable. So having reliable computational models that can predict how stable any given protein is as we make modifications to it can help save experimental time and cost in the development process. We've worked with Schrödinger to bring you this webinar. We think it's packed with information that we think you'll be interested in from absolute experts in the field. Today's speaker is Guido Scarabelli. He's a senior scientist at Schrödinger with a background in computational characterization of a variety of biological proteins, from antibodies to peptides and motor proteins. So I'm just going to invite Guido to turn on his webcam and we can get on with the presentation. Hi, Guido, I can see you.
Hi, Phil.
Brilliant, we can hear you as well. So please do go ahead with your presentation.
Okay, let me play from start. Okay, so thanks, Phil, for the nice introduction. And as you mentioned, today we're going to talk about the use of computational methods to predict the effect of mutations on protein thermal stability. Now, why are we doing that? Because protein thermal stability is a key factor when you work with any type of protein, and it is directly or indirectly connected to many other properties. For example, if you have antibodies and they have to, using quotes, survive on the shelf for a few weeks, you want those antibodies to be stable. You might want also that they do not aggregate or do other things, but the stability is important. The enzymatic activity for enzymes, for example, some enzymes, they might work at specific condition of pH or high temperatures, and again, they have to be to be able to function and work in those peculiar conditions. Or even the expression of proteins. When you express proteins, you want them to be stable and not fall apart. There are many techniques, experimental techniques, that can be used to determine the thermostability of proteins. For example, here I listed a few of them: differential scanning fluorimetry, circular dichroism, FRET, and so on. Just to give you an example, with the DSF, what you can do is to take your protein, mix it with a fluorescent dye, and then increase the temperature. As you can imagine, when you increase the temperature, the protein starts to unfold and starts to expose hydrophobic residues that usually are present at the core, in the core of the protein. The fluorescent dye will interact with those exposed hydrophobic residues, and so you can measure in this way the unfolding of the protein. And you can repeat this experiment with wild type and variants of the proteins to get a difference and see how the variations that are introduced in the protein will affect the thermostability. Now, all these techniques, they kind of require reagents, so there is a cost associated to that, and there is also the time that you need to use to run the experiments. Therefore, the goal of computational methods is basically to reduce the cost and time associated to those experiments. And that's the kind of general goal that we have at Schrödinger, not just for protein thermostability, but in general for all type of computational calculations that we can run. Now, at Schrödinger, we also focus on physics-based methods. And with that, I mean methods that require in input the crystal structure, or at least like an homology model, so 3D coordinates of your protein. So each atom has to have like a X, Y, and Z coordinate to describe its position in the Cartesian space. And besides that, there is also the use of a force field that is basically describes the interactions, the strength of the interactions formed by the different atoms in the protein, or ligands, if you have ligands present. So today I'm gonna mainly talk about the use of free energy perturbation calculations, and I'll give you a little bit more details on that, like in 1 or 2 slides. But I'll also present a few results using another technique that is still physics-based, which is called the MMGBSA. The difference between the two, FEP and MMGBSA, is that FEP is more computationally intensive, so it is based on molecular dynamic simulations. So it takes at least, it might take a few hours to run on a GPU, while the MMGBSA is faster because it has more approximations. So there is no dynamics involved, and the solvent around your protein is not physically represented by atoms like in FEP calculations, but it is represented by a function, so it's called like an implicit solvent. Because of that, it is also, there are more approximations in MMGBSA than FEP, and therefore it is less accurate. But I'll show more results on these two techniques later on in the talk. So about free energy perturbations. These type of calculations, they are based on a thermodynamic cycle, which is represented in the figure on the left here. So what we have here is the green oval is the folded state of our protein. The green kind of loopish representation here is the unfolded state of the wild-type protein. And then on the right, we have the folded state of our mutant and the unfolded state of our mutant in the bottom right. Now, ideally, with our calculations, what we would like to run are the transformations represented by the arrows 1 and 2. So you have your folded wild-type protein, and you unfold it in the simulations to reach the unfolded state. You get the energy of the transformation, and then you repeat the same for the mutant protein, and then you compare the energies of the two and see if your mutation is affecting, I mean, how the mutation is affecting the stability, if it's making your protein more stable or less stable. Now, unfortunately, these type of transformations cannot be run with the current computational power that we have. And there are different reasons connected to that. I'll mention just one or two. So as I said before, in FEP calculations, the solvent is physically represented around your protein. So you can imagine that if you have a folded protein, you can actually, and you start, that's your basically crystal structure, that's your starting conformation, you can get a pretty good idea of how much solvent you need to be placed around your protein. But when you go to the unfolded state, the shape and the volume of your protein will change. And so to basically accommodate the different conformation that you can have here in the unfolded state, you will need a much larger box. And so many more water molecules present around your protein. And as you can imagine, the higher the number of atoms you are simulating, the longer the simulation will take. And therefore, this will make FEP calculations very impracticable. It won't be reasonable to run this type of calculations. It will take too much time. And in addition, you will also need to, if you want to do that, you will also need to properly sampling the conformational transitions among the different conformations of the unfolded state, and that also requires a lot of time. Therefore, what we do in FTP simulations is a kind of trick. So we are going to start with our folded state, wild type folded state, and we're going to change it into the mutant still in the folded state. So there is no unfolding event in our simulations here. And then we repeat the same on the unfolded state. So we change the wild type residue into the mutant one. Now, this is done across a series of molecular dynamic simulations. So it's not only one simulation, it's a set of them. Usually the minimum that we use is at least 12, but you can use more depending on the type of transformation you are performing. And what you get then is the energy, what you calculate is the energy difference between these two transformations to get the delta G of binding. Sorry, it's not binding, it's, in this case, it's stability. Okay, now I just want to show you a representation of what's happening in an FEP simulation. So this is a movie. It's not, the frames are taken from real simulations, but again, remember that we have a set of molecular dynamic simulations, not just only one. So this is basically a representation. And as you see, so let me play this again. So we start with a wild type residue. I think that's an isoleucine, and then we slowly transform it into a methionine. And the transformation is performed by turning off the electrostatic and van der Waals contributions of the atoms of the isoleucines, and then slowly turn on the van der Waals and electrostatic contributions of the atoms of the methionine in this example. And so that's basically what we do in an FEP simulation. Now, so as Schrödinger, the energy perturbations have been around for a while. We had the tools to perform these calculations for like a good number of years now. And originally they were developed for to study small molecules bound to proteins. Now, in 2017, we had the idea of, okay, let's use the tools that we developed for studying different ligands bound to the same protein to mutations of residues, because I mean the physics behind the two problems is the same. So we could apply basically the same tool for studying the mutation of proteins. And these are the results that were obtained. So my colleague Thomas Steinbrecher, he took 10 proteins with known characterized mutations, known effect on the thermostability, and there were more than 700 mutants in total. And the results that he obtained was an R-square. When we compare the predictions of FEP with the experimental values, he got an R-square of 0.47 and then root mean square error of 2.3 kcal per mole. Now, these results are not, we can say that they are okay. They are not super great. However, this work was really important because it highlighted what we needed to change in the simulations to improve the performance of the calculations. Because here, so the black points, those are neutral mutants. It's like the one that I showed before in the movie, where the side chain of the wild type and the side chain of the mutant have the same charge. The red points here instead, they are charge changing mutations. So your wild type side chain has a different charge than the mutant. For example, you mutate the isoleucines into an aspartate. And as you can see here, especially in the top part of the plot here, that there are a lot of charge changing mutations that are not predicted well. So the prediction of FEP calculations differ a lot from the experimental values. And so we understood that we needed to change something in the code and in the way we run the simulations to improve the performance on charge changing mutations. And this study, together with other studies performed on small molecule FEP, so FEP applied for studying ligands and proteins, basically resulted in a series of improvements through the past 4 or 5 years in the FEP code. And these are the main ones here. So first of all, there was what we call an alchemical water approach introduced when you have charge and mutation, so the ones that Thomas wasn't able to predict very well. And the change consisted in, so when you mutate a residue, and for example, a neutral residue into a positive one, at the same time in the bulk water in the simulation box, there is a water molecule that is mutated into a counter ion. So the total charge of the two systems is the same, and this allows to prevent artifacts created by having two systems with different charges, which was partially what was causing the bad predictions before. So that was the first improvements that we made. Other improvements, they are related to the treatment of dissolution, also to the presence of water molecules around the mutation site. So the figure here is represented, it's like I took it from the paper. So it's basically showing the small molecules bound to a protein, but the same concept applies for protein mutations. Because, so let's imagine that you have, for example, a huge residue with like a big side chain, like a tryptophan. And this tryptophan is partially buried, and it is mutated into a residue with a smaller side chain, like an alanine or a serine. Now, what can happen in these cases is that you create a cavity that in the experiments, the cavity is going to be filled by water molecules. But to mimic this phenomenon, this process of like filling a cavity with water molecules in our simulations will take like long simulations, because I haven't mentioned this, but by default, FEP simulations, they are, so each MD simulations in an FEP calculation is like 5 or 10 nanoseconds long. So they are kind of short MD simulations. And therefore, filling a cavity with water might take more time. So to mimic that process, what we did was to introduce a grand canonical Monte Carlo algorithm during the simulations, which tries to insert or remove water molecules around the mutation site to basically mimic the solvation of those cavities. And that improved the prediction of mutations in those situations. Another improvement that we made was to allow the option to introduce proline mutations, because, so you know, proline is a kind of peculiar residue. It has like two covalent, between backbone and side chains, there are two covalent bonds. And that causes inaccuracies in the calculations if you use like a standard FEP approach. So what we introduced here was to basically use what we call a soft core bond potential, in which the stretching, the terms connected to the stretch of bonds, the harmonic term in the force field, is being modified to accommodate the modification of two covalent bonds at the same time. And then we also introduced like the possibility to mutate to non-standard amino acids. So this was not present when Thomas done his calculation in 2017. It did not affect any of his results, but it is a nice update to have in case people want to introduce mutations with non-standard amino acids. And finally, the most recent update has been the a change in the representation of the unfolded state. Because as I was mentioning before, the unfolded state is kind of critical for the simulations. And remember, we cannot simulate the fully unfolded state of the protein, because this is going to require like a huge box with many atoms and like a very long simulation time. So what Thomas used in his calculation in 2017 was to use a single residue to represent the unfolded state, which is a huge approximation, probably the biggest approximation that you can make for the unfolded state, because you have only one residue. but allowed the calculations to be finished in a reasonable time. Now, last year, what my colleague Jianxin Duan and Dima Lupian, what they explored was, okay, let's try to represent the unfolded state with more residues, okay, to see the effect that we have on predictions. So what they did was to select 80 mutations from another data set that was, again, experimentally characterized, so they knew the experimental delta G's, and so they could see how the simulations performed. And what they did was to use the unfolded state representation model that we had before with one residue, the one that Thomas used in 2017. And then they also tested different unfolded state models using 3 residues, 5 or 7 residues. And the other residues that are added, they are coming from the protein. So they are not, for example, all alanines. They are the real residues present in the neighboring residues present in the protein that is studied. And what they observed, as you can see here from the plot, looking at the mean unsigned error and the root mean square error, is that when you move from the single residue to the 3 residue unfolded state representation, you have a lot of improvement in the predictions. And actually, so the improvements, they also, you have more improvements even when you basically increase more residues. But what we chose as default in our simulations right now, so if you use the Schrödinger software to run this type of simulations, what you have right now is the representation of the unfolded state with 3 residues. And that's because also we wanted to limit the amount of time required to run these simulations. And so this the 3 residue unfolded state representation was the best compromise between improving the predictions and keeping the time as short as possible to run these calculations. Now, these are the results that Jianxin and Dima obtained, and then this paper was published last year. So they simulated 80 mutations from a published dataset by Fabrizio Pucci in 2018. And they added a few more proline mutations to that dataset. So in total, I think they had around 90 or a little bit less than 100 mutations. And as you can see, so the R square is 0.66 and the RMSE is 1. Let me reduce this thing here a little bit. So it's 1.1 kcal per mole. And so it's much better than what Thomas obtained in 2017. And for those of you who are wondering, okay, what are those dash vertical lines in the correlation plot? So that is connected to the outlier analysis of FEP calculations, which is what internally at Schrödinger we always do when we run retrospective FEP calculations. So we know the experimental results. We just want to see if our model is good enough to be studied with FEP to reproduce the experimental data. You're basically going to look at what's happening in the worst predictions that you have in your plot to see if there are some conditions that in the simulations or something that you can change to improve those predictions. So what Dima and Jianxin did was to basically change, like it can be the simulation time, it can be the number of MD simulations using the transformations, it can be the initial structure to basically improve those predictions. So these results here, I think they refer to the, let's say, outlier corrected plot. But I won't go into the details of describing what they change in those cases, but I will show other examples that I have on more simulations on this data set. And how we basically solve those outliers there. But if you are interested in the discussion of those cases, you can also look at the paper. There is like a detailed description of those outliers there. Okay, so what we did then was to extend the work that was done by Dima and Jianxin, because in the data set published by Fabrizio Pucci in 2018, there were more than 300 mutations. So Dima and Jianxin last year, in the work published last year, what they did was to select the mutations that were characterized at a pH that was close to be neutral, so around pH 7. And they got 80 mutations from the dataset. The remaining ones that were characterized mostly at acidic pH were not included in the Yanshin and Dimas study. So what we did was then, okay, let's consider these other mutations that we didn't include initially and see how FEP performs on those cases that were characterized at acidic pH. So that's what we did. We included in the end 328 mutants from that data set. And of those 328, there were 41 of them that have experimental delta G of 0.5 and minus 0.5 kcal per mole or lower. And we use this cutoff as to classify stabilizing mutations. I mean, of course, you can argue that, okay, why did you choose minus 0.5? You could choose minus 1, for example, and that's a reasonable argument. So in the slides, I'm going to show you the results with this value here, but the same trend applies if I was showing the results with minus 1 kcal per mole. Just you would have had a lower number of stabilizing mutants. Oh yes, one other thing is that, so in this data set, there are 62 mutations that involve a charge change transformation. So the cases that Thomas Steinbrecher in 2017 was not able to predict very well because of the limitation of the code, okay? So I will show you also the performance on those cases. Okay, so these are the results that we got on the 328 mutants on that data set. As you can see here, so we colored in blue with a blue square the charge changing mutations, and with a green circle we have the neutral mutations. So the numbers are similar to what Yanshin and Dima obtained in the paper published last year. The R square is 0.65, the MUE is a little lower than 1 kcal per mole, and the RMSE is 1.25 kcal per mole. So those numbers were comparable to what has been obtained with just a subset of the dataset. And if we look at the distributions of the mean and sign error, 2/3 of the simulations in the dataset, they had an MUE that was lower than 1, which is really good, but 1/3 of them had an MUE of that was higher than 1. And so what we did, and I'm going to show you in a few slides, it was to look at some of those cases to see what went wrong in these predictions and what we could have done or what we could do to address those cases. But before doing that, I just want to show you a quick comparison that we made of among protein FEP calculations and the MNGBSA. So if you remember, the MNGBSA is still a physics-based method, but that is much quicker to be run compared to protein FEP because it has more approximation. There is no there are no molecular dynamic simulations involved in the MNGBSA, and the water is represented implicitly. The method in the central column of the table is a kind of hybrid combination between the MNGBSA itself and MD simulations, because so what we did was let's try, so the idea that we have was let's try to introduce some dynamics or at least some structural ensemble with the MNGBSA, because this one is run on the single crystal structure. Okay, so here what we did was to take the crystal structure, run a short MD simulation, it was 10 nanoseconds, and then cluster the trajectory, obtain the most tempo-populated clusters, and run the MNGBSA on those clusters, and then average the results. So computationally speaking, the method in the sender is it takes longer time to run compared to the MNGBSA, but it has some dynamics introduced, and we wanted to basically see the effect of that, if it was really improving the results of the MNGBSA or making them worse. So, as you can see, in terms of the true positive, and remember, we use minus 0.5 kcal per mole to identify the stabilizing mutations. So we had 42 stabilizing mutants. FEP is able to identify 31 over 42 stabilizing mutants correctly. The MNGBSA and the MD-MNGBSA, they had a similar performance, and they identified roughly half of them. The MNGBSA itself, a little less than half also. But all the three methods, they were basically identifying the same number or a very similar number of true negatives. And more or less, we can say that also the false positive and false negative, they have the same trend as the true positive and true negative. So protein FEP, as you can expect also, because it's it's more accurate as a method, it has a better performance than the MNGBSA and the hybrid MD-MNGBSA method that I'm showing here. But keep in mind again that protein FEP for one simulation, it can require like 5 or 6 hours on a GPU, while the MNGBSA itself, it requires maybe 1 minute or 2 minutes on your laptop, so that can run on a CPU. So it's much, much faster, but it's less accurate. Okay, then we also had a question about the effect of the pH that was used in the experiments to characterize the mutations on FEP calculations. We wanted to see, okay, maybe is there like a specific value of pH that FEP is not able to predict well? And so here you can see the RMSE results of FEP calculations according to the pH range, and we see more or less like a similar trend, so that there isn't a specific pH range that FEP is like performing badly or one that is performing super like extremely well. It's more or less the same across the range, even though keep in mind that so in the square brackets here, I'm showing the number of mutations in this pH range. So having an RMSE of 1.2 on 13 mutations is probably less meaningful than having an RMSE of 1.3 on 134 mutations. So keep in mind that like this, for example, this group here has few mutations. However, we observed that the pH used in the preparation of the structure was really important for the quality of the results of FEP simulations. And I'm going to show you a couple of examples here where depending on the conditions that you use, FEP can perform well or not so well. Oh yes, sorry, no, before doing that, I forgot that I need also to talk about the 62 charge changing mutations, and the results we got like an R square of 0.6667 and an RMSE of 1.55 kcal/mol. So these numbers are better than what Thomas in 2017 obtained with charge changing mutations, because of course there were all a set of improvements in the FEP code. But still, if you look at the RMSE of 1.55 and if you compare it with 1.25 that we got on the whole data set, still it indicates that charge changing mutations are a little bit more difficult to correctly predict compared to neutral mutations. And that's because basically the different introducing a charge or removing a charge in the mutation process is still like a kind of complex problem to simulate properly. Okay, going back to the closing the parentheses and going back to the pH importance. So in this example here that I'm showing, we have the residue 96, which in the wild type is an arginine, and it is mutated into an aspartate. So we go from a +1 charge to a -1 charge in the mutant. Now, if you set up the simulation and your mutant side chain will have a -1 charge, the prediction of that mutation will be, with FEP, will be 9.7 kcal/mol. The experimental value is 3.5. So FEP predicts the mutations as highly destabilizing, and that's in agreement with the experimental value. But if you look at the number, there is a huge difference. There is more than 6 kcal per mole difference. And therefore, what we did was then, okay, let's generate a model of the mutant structure, of the aspartate present in position 96, and calculate the pKa of that residue. And when we did, we observed that the pKa predicted of the aspartate 96 mutant in that position, so for that aspartate was 6.3, and then the experimental pH used to characterize the mutations on the experiments was 5.4. So you see that there is less than 1 log unit difference between these two numbers, and that indicates that potentially we should have basically used like a different approach in our simulations. And so what we did was, okay, to run one simulation with the charged form of the aspartate, but also we ran one other simulation in which we mutated the arginine into a neutral form of the aspartate. And then we used a script to combine information of the two simulations and get a prediction of that using both forms basically of the aspartate, charge and neutral. And when we did that, the numbers of the delta delta G predicted by FEP was still destabilizing as before and as the experiment, and the numbers were was much closer to the experimental value than using just the aspartate in the charge form. So that's one of the cases in which you need to be aware of the importance of the protonation state of your mutant side chain. Another example here, it's a little different, but it's still related to the neutral or charged form of residues in the simulation. And so here we have this protein that has 3 mutants on position 20. So the wild type residue is an aspartate, and the mutants, they were either an alanine, an asparagine, or a serine. So experimentally, the mutation to an asparagine was favorable, was making the protein more stable. The serine also, you can argue that it's kind of borderline. Depending on which cutoff you use, you can classify that as stabilizing or neutral. While the mutation to an alanine was basically neutral. It had a very little destabilizing effect. Now, in proximity of the mutation site, but not directly interacting with the residue number 20, there is glutamate in position 11. Now, if you simulate the FEP calculations with a charge form of glutamate 11, these are the numbers that you obtain. So all 3 mutations are predicted to be highly stabilizing, so highly favorable if you want to make your protein more stable. And if you look at the numbers and compare them with the experimental values, they are kind of different. I mean, there are huge differences, like around 4 kcal per mole each. So these predictions, there is something that we needed to do to improve the numbers obtained by those predictions. And the first thing that we tried was to look at the pKa of glutamate 11, look at the pH using the experiment, see that they were very similar, and so we rerun the simulations using neutral form of glutamate 11, and the numbers improved around 2 kcal per mole for each mutant. But still, they were kind of different from the experimental numbers. So there was something else going on in this system that was preventing FEP to reach, to predict numbers that were similar to the experiments. And so then we looked at the conformation of the initial structure that we use for input for FEP simulations. And we observed that the one that we used at the wild type residue, the aspartate 20, the side chain was basically oriented in one way and was forming hydrogen bonds with neighboring residues. But then there is another crystal structure of the same protein in which the aspartate 20 has a different side chain orientation, and those hydrogen bonds are not formed. In addition, we also run like a quick normal mode analysis to see the global movement of the protein structure. And we observe that there are two kind of domains into this protein that can like open and close. And so what we did was to manually rotate the side chain of arginine 145 to basically put it closer to the side chain of the mutation site let's say in the open form, so not when hydrogen bonds are formed with neighboring residues by the side chain of aspartate 20. And then run the simulations. And we observed that basically the structural modifications that we made in the input structure had an effect on the predictions. And this resulted basically in improving the prediction of 2 of the 3 mutants. So the mutation to alanine, it reduced, so the number predicted was smaller compared to the original simulations that we ran before all those corrections, but still, so it gets closer to the experimental value, but still it's not a correct prediction. The mutation to the asparagine instead, that is correctly predicted, and the numbers, they were comparing the predictions with the experimental value, so the difference is 0.5 kcal per mole, which is in the range of the error, so that's a good prediction. And the last prediction instead was not affected at all by, or basically not affected by the structural modifications that we made. Therefore, so there is something else going on in the systems that we were not able to really capture. Maybe it's connected to the movements of the protein. Maybe we needed like longer simulations. We haven't tried to run longer simulations. And so, as you can see, the conditions that you use in the FEP simulations will affect your results. So that's something you need to keep in mind when you run this type of calculations. And finally, what we wanted to do was also, so we basically had the idea of having a kind of workflow in which you can use a fast and quick method to screen hundreds of mutants or thousands of mutants, and then select maybe 30 or 40 mutants that can be studied with protein FEP. That's because, again, if you have the time and the resources to run FEP calculations on hundreds of thousands of mutants, you can do it, of course, but might not be really feasible. And therefore, that's why it can be useful to use, when you have that number of mutations to study, it can be useful to use a quick method to quickly screen a lot of mutations and then select the most promising one and characterize them with protein FEP. So because we had the MMGBSA results, that's what we try to use in this hypothetical workflow. And what I'm showing here in the plots is that, so if you're using the MMGBSA on the full data set, and we use -0.5 kcal per mole as cutoff to select stabilizing mutants predicted by the MMGBSA, these are the numbers that we obtain. We will obtain 78 potential stabilizing mutations. And of those 78, 18 of them are correct. So 18 of them are really stabilizing. We know that because, if you remember, we have the experimental value of those mutations in the data set already characterized. And that's probably, for this data set, this indicates that this is maybe like the best cutoff that you can use for MMGBSA, because increasing the cutoff will increase in the number of mutations suggested by MMGBSA, but wasn't really improving too much. So it was improving like a little the real stabilizing mutants present in the suggested mutations. And the comparison between MMGBSA and the hybrid MD-MMGBSA didn't really show any significant difference either. So in this example, we use MMGBSA, but of course you can imagine that you can use any machine learning methods, for example, or any other quick way to assess thousands or hundreds of mutants instead of the MMGBSA itself. And finally, I want to show basically current work that is almost complete on homology models, because so again, in the data set that I presented you in the previous slides, we had crystal structures. But then we had the question of, okay, let's say that we don't have crystal structures. how well does perform FEP on homology models. And so this work has been performed and is almost completed by Mu-Yun Lian, who's a grad student at Urbana-Champaign, who joined us in last summer for an internship, and basically in a little more than 2 months he did a great job and completed this analysis. And what you can see here is that of the structures that we used in to study the FEP calculations, some of them had a single template that can be used for building homology models, and that's the sequence ID, the percentage sequence ID. Other structures, they had multiple templates. So one of the key aspects that Mu-Yun analyzed was in the case where you had more than one template, how good the template can be to obtain good results with FEP calculations. And these 2 plots are showing the comparison. So here we have the crystal structure analysis. It's very similar to what I showed you before, just there are a few number of mutations because some of the proteins didn't have a template to, and so was not for homology models, and so was not included in Mu-Yun's analysis. Also, what Mu-Yun did was pointing out the protein mutations present in the data set, besides the neutral and charge changing mutations. And these are the results that he obtained with FEP calculations on homology models, on the homology models built with the best template available. And as you can see, so the numbers are similar. So the R-square is a little lower compared to when you run FEP on crystal structures. And that might be connected to the points shown here that are kind of affecting the R-square, probably. But the MUE and RMSE measurements, they are very similar. So when you have a good template with a good similarity between your sequence and so the sequence of the templates and the query for the homology models, they are good. They have a good similarity. You can basically obtain good results. That was one of the main conclusions. And the other one is that so it is important to look at the similarity, not just of the whole sequence when you build homology models and you want to use them with protein FEP, but it's more important to look at the local similarity. Because you can imagine that if you want to choose a template to build a model and you want the mutation site that you want to explore as a poor similarity, very likely the results that you get with FEP, so you're not gonna build a good model, and very likely the results that you get with FEP, they won't be good. On the other hand, if you might have a template that has maybe an overall 30% sequence similarity, which can be borderline, but in the mutation site that you want to explore, there is a good conservation, then you can actually run FEP calculation and obtain good results, because the differences between your template and your query sequence, if those differences are far away from the structural point of view of the mutation site, very likely they will not have an effect on FEP calculations, because what we are going to measure there is kind of in FEP simulations, again, we have a short MD simulations of 5 or 10 nanoseconds, so the effect of residues that are far away from the mutation site is kind of limited, and so that's why you can ignore in the similarity differences when building homology models for FEP simulations if those residues are far away from the mutation site. Okay, to conclude, so what we show is that we can run protein FEP calculations and have a good agreement with experimental thermostability. And also FEP is able to deal with mutations that have been experimentally characterized as acidic pH. However, there are some caveats to remember when you want to run this type of calculations. For example, when you are charge changing mutations, you need to be careful of the protonation state or the neutral or charge state that you're going to use for a mutant side chain. And that has basically to match your experimental conditions, because otherwise, if you don't have a match with the experimental conditions, your predictions will be not correct. And also the quality of the crystal structure or homology model that you use in input for the FEP simulations is important. Because again, we use MD simulations, and so there is a dynamic sampling. And we also, so I haven't mentioned that, but there is like an enhanced sampling procedure applied during FEP simulations. But still, if you want to sample, for example, if you want to mutate a residue in a loop that opens and closes a lot, that should open and close a lot during simulations, this type of movement, like loop opening and closing, will not be sampled in FEP calculations, and so your predictions might not be correct. So that's also something to keep in mind. And then if you want to run FEP calculations, as a general recommendation, we always say to use first a retrospective small data set to check that the simulation conditions that you want to use are working fine. Because basically you can evaluate, if you have experimental data available, you can run, for example, 20 mutants and see if your FEP calculations are able to reproduce those 20 already characterized mutations. And if everything is fine, then you can move forward prospectively and use FEP calculations to predict new mutations that have not been experimentally characterized. But if instead, in the retrospective validation of those 20 mutants, you don't get good results, it means that you need to change something in the simulation conditions, in the structure use or other things to before moving in for with a prospective calculation, because otherwise you basically waste resources if you move directly on a prospective calculations when you don't have a good model, basically. Okay, with that, I finished, and I'd like to thank you all for your attention, and I'll be happy to answer any questions or try to answer the questions that you have.
Brilliant. Thanks, Guido. That's a really interesting talk. Thanks very much. Okay, so we have got a few questions coming in. Just remind everybody who's watching, do please keep putting your questions into that questions box at the bottom of the GoToWebinar panel. We would like to answer as many of your questions as possible. That's why we've got Guido here. So do keep putting those in, and we'll kick off with the first couple. So the first one that I have is a question from Maciek, and he said early on in the presentation you were talking about the initial kind of work you did on FEP in about 2017, and then an improved version in 2020, and you showed some different data sets that were modeled using those. Do you know if your colleagues who were doing that research went back to the original 2017 data set with the improved version and checked it to see how that performed against with that original data set?
That's an excellent question. So between the two data sets, there is some overlap. So some of the mutations are the same, but not all of them. And we haven't tested yet the improvements in the code with the old data set, the one from 2017. And the reason is that, so when Thomas in 2017 built the data set, there were some biases in the data set. For example, there were a lot of alanine mutations. Most of them were, like the great majority of those mutations was destabilizing. And these are also kind of common biases present in the experimental data set that are built for characterizing the protein thermostability. That's why when my colleagues, Dima and Genshin, did the work in 2020, they chose a new data set that was published. They tried to address those limitations, so try to limit the number of alanine mutations present, try to have like a good quality crystal structure. So for sure we can say that the new results presented with the new data set, they are on a curated set of structures, and so they represent a good or at least a very well structurally behaved case. If your structures are not so good, for sure the predictions will be affected by that. Okay, and that's the case that probably, so again, we haven't done the calculations. What I expect is that if we take exactly the same mutations that Thomas studied in 2017, the results might be not as good as the ones that we got in 2020, but they will be better than what we got in 2017 for sure.
Yeah, and I guess that's partly making the data set most relevant to the kind of thing that you're looking at as well.
Yeah.
Great. So the next question comes from G, which is, could this kind of FEP and simulation method that you've described be applied to membrane proteins? Obviously, there's a lot more complexity around the kind of solvation of those kind of things and the interaction with the membrane. Is that something that can be done?
Yes, definitely. We have protocol to basically set up FEP simulations with membrane proteins. It has been extensively used to study ligand binding, so the delta G of binding of ligands to membrane proteins. I don't know if it has been studied for like characterizing protein-protein interactions or the stability of proteins. For sure not stability. Maybe there is a paper that just came out a few months ago in which peptides binding membrane proteins were studied with FEP, but I need to double check that. But for sure, we use it extensively to study ligand and GPCR binding.
Brilliant. Okay, and we've got a question from Stuart, which is, can you use this method to identify novel stabilizing mutations, and how can you identify the best stability mutations given the large number of potential possibilities?
Yes, so that kind of refers to the hypothetical workflow that we imagine, that I presented in one of the final slides. So again, because you have so many possibility to introduce mutations, and you can think that not just the 20 natural amino acids, but if you want to use also non-standard amino acids, you have many more possibilities to design residues to stabilize your protein. So it would be ideal to have like a quick method to screen and to screen hundreds or thousands of mutants and to remove the destabilizing ones, and then use FEP to characterize the potential stabilizing ones that you have. So yes, you can do it. Of course, so the numbers that you get are connected to the stability that you get. So the more negative delta Gs that you get, the more stable your variance should be. That's the prediction.
Perfect. Thanks very much. Okay, so something else that's kind of occurred to me is we've seen in the last year or two some really exciting developments with things like Google's AlphaFold and predictions of protein structure and folding. Can you give us some idea of the compatibility of those kind of models with FEP calculations? You talked about crystals and homology models, but can you go into some of that kind of data?
Yeah. So Mujin, the person that did the homology modeling work, he also started to look at structures from AlphaFold 2. And the conclusion, so he didn't look at all those mutations. He just, well, last time that I spoke with him, he mentioned that he looked at like 2 or 3 models from AlphaFold. And he said that in one case, he got very good results. In another case, he didn't get good results. But when he compared the AlphaFold model with the crystal structure, because the crystal structure is available, he observed that there were side chain placement differences between the two. And so the AlphaFold model didn't place correctly all the side chains. They were not oriented in a proper way. And that's why like a standard FEP calculations of 10 nanoseconds was not able to reproduce very well the experiments in that case. One thing that we can try in those cases, I don't know if Muyun tried that or yes, still to do it, is to maybe extend those simulations, maybe do 50 nanoseconds for each MD simulation in the FEP ensemble, and see if you can basically adjust your sidechain orientation and modify that from the initial one, and so improve the predictions. That's one case. So in the end, again, it depends on the quality of the model produced by AlphaFold. Sometimes it worked well. In one other case, it didn't work well.
Okay, that's great. And I think we've got time for just one more question, which is, can you give us an idea of the advantages and disadvantages of protein FEP in comparison with sort of machine learning methods to predict these kind of stability effects?
Yeah, sure. So this is kind of ties up with a question that was asked before, and the biases in the databases. Because, so for machine learning, you will need to select a training set. And if you look at the currently experimental data available, there are biases present. Alanine mutations are very common, and also destabilizing mutations are very common. That's connected to the nature of introducing mutations. It is much easier to introduce a mutation that destabilizes your protein than stabilizes it. And therefore, when you build a machine learning model, you need to kind of mitigate those potential issues and to come up with a good prediction model. But on the other hand, the advantage that you had when you use a machine learning model is that once you train it's fine. And you can use quickly to predict like a huge number of mutations. FEP instead, it doesn't have any bias, so there is no training in FEP. So it doesn't have any bias connected to training. But it takes more time. So you need a GPU to run those calculations. So that's a disadvantage that we have with FEP calculations.
Okay, so I guess it's one of those things. It's always a trade-off between the information that you have and the information that you need, and the level of precision that you want the model to kind of deliver. Brilliant. Okay, well, thanks very much, Guido. I think you've done a really good job of answering those questions there. I think if there were more questions that we didn't get around to, there may be possibility to answer some of those offline. But thanks very much again. I'd like to thank Schrödinger for sponsoring the webinar. It's really important that we kind of work together to bring you these kind of high quality things. We've had a few URLs go out in the chat function, so do grab those before the webinar ends if you want to be able to remember what they are, because they will disappear, or you can obviously check back on the recording to see what they were. Thank also to the audience for attending. You are the main reason for us doing this, and I hope that all of you got something useful from today's webinar. If you did, just do remember that you will get a link to the recording in a couple of days' time, and you will get your certificates of attendance in that same email. And if you liked this webinar, then do check out chemistryworld.com/webinars to see what other topics are coming up. And I hope to see you in another webinar very soon. I'm Phillip Broadwith, Chemistry World's business editor, and we shall see you again very soon.